Welcome back to Advent of Code, and today is day 10. This is it, two number digit. We've reached day 10. So in this one we have a bunch of adapters that have to add. We have to find a difference between like two adapters that are consecutive or something like that. And the prime statement is quite complex, but what I felt, so first of all, we always copy pasting this in here, and here we've got all of our numbers. So let's run that right away. I found something interesting, which is that, oh wow, we need day 10 here. So this is the code that I'm always using for each prime statement to just pass the input. And here we can see we have like everything correctly. We want to start from the voltage that is 0. This is important. So basically what I'm thinking about is we should say line is equal to we start at 0 dot concat with the rest. So now we should have like the first one, and then we have all of these that should be in the right order, but we know that we're using all of these. So one thing that I was thinking about is, what if we just sort them? Oh yeah, of course, because there are digits in JavaScript, we have to do this little dance from the lower to the biggest. And here we have everything sorted, which is pretty nice, because now we can just do the difference between the current one and next one, or the next one minus the current one, and we find that here there is a difference of 1, and we need to count that. Basically here they say we take the adapter rated 1 jolt and the difference is 1. So this is exactly what we care about. We just have to go over each of these. So for let's say traditional for if, so let I equal 1, I below length, or lines.length, and I plus plus. And here we have to count actually the voltage 1 and voltage 3. So here we're going to have like something that we call difference, and this is going to be equal to lines of I minus lines of I minus 1, because we start at 1. The first element is going to be lines of 1 minus lines of 0, so we are not out of bounds of this array, so everything is good. And now we check if diff is equal to 1. In that case we say voltage 1 plus plus. If diff is equal to 3, voltage 3 plus plus. There is one other thing that I noticed when I was reading this right before the video, which is that where was it? Yeah, we have a built-in voltage adapter rated for 3 jolt higher than the highest rated adapter in the bag. So this is one thing that's important, is that we have to add another one here, which is, we're gonna just add it at the start here. And actually, what do we need to output? We've got those two counters. Yeah, the number of 1 jolt difference multiplied by the number of 3 jolt differences. So basically, we just log voltage 1 times voltage 3. And if we node day 10 again, we have 35. I believe they don't give us exactly what we care about. They just say, oh here they don't tell us anything about it. So we're going to take this one instead, the larger example. And we're going to check if our result is correct. It's always good to check against this example. And here we need to, they don't give us the final answer, they give us voltage 1 and voltage 3. So we're going to display everything 22 and 10. 22 and 10, we are good. So I think if we get the full input now, we should have something that works well. Let's go. We just run that. Have something bigger here. Oops, forgot to copy paste. Let's try that. I think that's good. Yes, we're good. Let's go to part 2. Okay, part 2. I couldn't read this, so we're going to read that now. We need to check if we have enough adapters. So here we have the first example, which is this small one here. So here we see all possible permutations, if I'm correct. No, all combinations. Yeah. So given the adapter from the first example, your total number of arrangements that connects to the charging outlet for your device is 8. Interesting. So we need to find how many ways we can order these in order to make it work. So I guess we can still use this ordered array, and basically we might be able to remove, for example, here we can remove the 5. Let's try to see here. Yeah, here for example they remove the 5, or they put a 6 instead. What is that? Okay, 1, 4, 5. You know what? Enough talking, we need to take this to understand what's up. So we're gonna paste that instead of the full input. And now after the first answer, we're gonna write part 2, and we're gonna do this calmly. And always it's good to understand the problem statement in depth, because otherwise you spend like so many hours just like going in a bad direction. Okay, so here we see that we have 1, 4, 5, 6, 7. So there is one time where they remove the 5, yes, and they also sometimes remove the 6. That's good. So we have the same setup, and I guess what's going to happen is that, wait. Let's read everything to the end. In total, this set of adapters can connect the charging outlet to your device in a lot of distinct arrangements. Okay, so I'm gonna be counting this. We're gonna be trying to remove one element and see if it still works. I guess that's gonna be it. And then we're gonna be, maybe you can do that recursively. I don't know if that's a good idea or not. But basically we can go over each of the elements, try to remove one, and then continue. That looks like an okay approach, although I'm guessing it could lead to some bad stuff in the end, because I don't know. You know what? Let's go and implement the recursive approach. So function we want generate all combinations basically of that. So we don't move them, but we can remove one or many of them. So let's say, and in the end, we want to, just understand all possible arrangements. So for sure, we need to keep the last one. Yeah, we do. Okay. Interesting challenge. So we're going to be doing this recursively, starting from combination of an array. Basically, if interesting, if array.length equal 2 or just 1, then we can't remove anything. There is just like, I'm not sure I'm doing the right thing here. I'm not sure it's going to be needed because we always have at least 3 elements. So I think that doesn't make sense. Let's not do that. But now what we need to do is we need to go through each element of the array and try to remove one, except we can't remove the first one and we can't remove the last one. That's going to be the challenges. Oh, we could be removing the last one. So here, for example, 49. No, we cannot because the end is 52. So now I think it's best to actually add the last one. So let me make it clear. I think it's not good to add here the voltage 3 equal 1. I think we need to do lines.push. So here we take the last element, lines.length minus 1, and we add 3 and we push that. So here, if we run that again, that was 3575. Okay, so we didn't change anything. The code is still the same here, except now we have all elements in the array. We have the 0 and the 22, and these two we know we can't remove them. So now we need to say const let result equal 0, and now we need to say for the current combination is one combination, so we need to start at 1, and then we need to let I equal 1 to I below array.length minus 1 I plus plus. So what we're going to say is we're going to remove the element I, and we never want to remove the element 0, and we never want to remove the element 19. Now we need to check. We're going to be doing the element removal here. So const array2, let's call that array2. I don't know, I don't have a good idea. This is going to be array.slice 0 to I, that we concatenate to array.slice I plus 1 to the end of the array. So this is removing the element I. However, we should only do that if array of I minus 1, no, I plus 1 minus array I minus 1. So what I want to say is we can only remove this element if the next element is the distance between the next element and the first element is below or equal to 3. So here 4 minus 0 is equal to 4, so we cannot remove 1, because at the maximum distance between two elements is 3. This is what is defined in the prime statement. But here, for example, 6 minus 4 is 2, so we can remove the element 5, and actually in the prime statement I believe they remove it at some point. Yeah, here there is no 5. Wait, here they remove the 5 here. So this is fine, we're doing a good job here. So this should be below or equal to 3. And the good thing is that the array is sorted, so it really helps us a ton. And now in that specific case, we can say, yes, remove that and check how many combinations. So result plus equal combination of array 2, which is a new array. So yeah, we're basically trying to do that. And then here we should just return results. So that's going to be, it might be a bit too intensive. We're going to try to see that combination of array. So for now, we have our smallest data set, which is this one here. And the answer should be 8. Let's try that. Oops, I'm going to have to fix that. Oh, here this is lines, which is the array that we've defined here. Let's try that again. This is 16. Eesh, that's not good. I think that was just 8 that we wanted. Interesting, so it's double the amount of time. So maybe we reach several times the same combination here, which is not cool. So I'm gonna have to fix that. What I'm thinking is that, yeah, we might be reaching several times the same combination, which is, yeah, definitely not a good thing. Let's try with the bigger example. This is a bit stressful because it looks like it's a lot more complex. Okay, this is taking forever. It's already taking forever while I haven't taken like the full input here. So it looks like we might want to avoid this duplicate HKs, or we might want to try memoization, which is a nice strategy that could be interesting. That would be really interesting. I think we're going to try memoization here. Hopefully this is going to speed things up like crazy. So here I'm creating a memo object, which is going to save everything. Because I'm not sending a second argument here, we're initializing the object to an empty to this array. Here we are also going to pass the memo object, so that we basically create the object here on the first call, and on each further call we are reusing the same object. So this is kind of a cache, you know. And here we need to store the result in the memo. So the only problem is that, yeah, I'm gonna do if array that join with a comma in memo, then actually let me create the key here. Const key is equal to that. If key is in memo, then memo of key, no. Here, if our key is already in the memo, then we return memo of key. That's what we need to do. And here, in the end, we need to do memo of key equal result. So basically what we are doing is using memoization here to speed up the computation, and here we get a huge number. I don't think this is the right one. That's annoying, because what is this? What did I get? So I should have gotten this number. Damn it. This number. I cannot paste it. Should have get 19208, and did I get like 208? I know what I get. I know what I got. I think I got something really wrong. Let's try to go back to our first scenario, because I went too fast. I had like a first scenario that was not correct, and I went to the second scenario. So not good. It's time to go back to basics. So one thing I can do is I can count the keys in memo here. I can say, oh, but memo. Here I can say object.keys of memo.length. Let's try to do that just for fun. Yeah, so actually this one is correct. So yeah, I don't know, but the result here is not correct, but I'm storing all the possible values, all the possible combination in the memo object. So I guess we're just gonna use this hack. That's a bit of a hack, but if it works, let's try. So here we have the correct solution, yes. What I'm afraid is that this little hack that we're using is not going to be fast enough for the full data set. Yep. This was a bad choice. So we've got one solution here that is not working, because we're like computing over and over some possible options. So I think I have an idea. I think I have an idea. So if we get back here, I think we're gonna comment out the memo part for now, because this is a bit too advanced and I don't think this is really good to use it, because we want to make it work first before making it fast. That's really how we should be doing things. So here, basically, we want, I think the problem is that here for the combination, we want to get rid of the element at the position I, but I think we want to get the array from I minus 1 to the end. I think that's mainly the problem here, because I was taking, I need to show an example. So here we have a good example. I was saying, okay, here we can remove 5. So now remove 5 and check all combinations that are possible here. But what we want to do is we say, okay, we can remove 5, so remove it and check all combinations that are possible here. And at the beginning of the array, it doesn't make a lot of, it's not really important. But here, when we reach the end of the array, when we say, I don't know, what can we remove? When we say remove 11, and if we check all possible combinations, we're going to be removing 5 again, and I mean, I don't know if the explanation was super clear, but I think it's gonna save a lot of time to only consider the end of the array. Let's try that. Maximum call size exceeded. Array slice I minus 1 to the end of the array. That's not good. It means that here we're like reaching a full loop where we keep having the same array here. So we're gonna have to give it a look. Oh, one more time we're using, we need to go back because we've made some mistakes. We need to go back to the simple test case because we are like making a lot of changes. This one, I think it's quite interesting because I think it's the first time that we're hitting a challenge that requires performance optimization. You cannot just like make it work. Okay, so here, as you can see, we keep having the same and same array. So here what I would do is I would print I here. Okay, I is equal to 1. Okay, so first of all, we have an issue, right? We don't have I. So we can and should be removing 5. That makes sense. However, oh no, wait. That's a stupid thing. We said we want to be removing the elements on the array on the position I. So here what we want to do is we want to say I minus 1 dot concat slice I plus 1. Basically we want to keep the 4 and we want to get all of the rest of the array here. So yeah, I minus 1 is the 4 and I plus 1 starts as 6 and goes to the end of the array. So that should be the right way to do that, to do it. Okay, now we have 6. The answer is 6, which is not correct. So that's annoying. Here, let's console log the array that we get as an input, and we get a bunch of array. So first of all, we get the full array, which is correct, the array from 0 to 22. Then we say we remove the oh, that's interesting. Here we got the full array, and here we get a 2 here. Where is this 2 coming from? Oh, I minus 1. It's array of I minus 1. So this is a bug where, like, you just need to pay attention to avoid these kind of bugs. So yeah, the 2 was not part of the array, so I was really wondering where it was coming from. It should have been, I guess, like a 4 or anyway. Let's retry now that we've removed this little bug. Okay, we've got 8, which seems to be exactly what we were expecting. We're expecting 8, I believe. Let me copy that as well. Now I'm scrolling. We should have gotten 8, which is the thing that we're getting. Now let's replace by the slightly bigger array. And okay, I should remove the console logs because otherwise I'm just gonna be wasting a lot of space here. And now we've got exactly what we want. Now let's get the full output. So see, it's really, I really feel that you need to go step by step and make sure you're solid on the basis. Then here I'm hitting the performance issue. So no worries, because we've got all our memoization set up. So I can remove that. Here I can uncomment console log, we don't care, but basically if we already computed this value, this combination, we return it, otherwise we compute it and we store it. Let's try that again. Memo is not defined. Yes, this one is not defined, that's normal. And now, as you can see, using this memoization technique helped speed things up like crazy. So there must be some theory around the memoization object and how it makes the complexity much smaller. But you know what? Let's just save that and verify. Yes, that's correct. I'm super happy. That's the first time I'm using the memoization technique, and it's really useful to make things faster, making your recursion faster, and it works only when you are computing several times the same state. And here it happens that, yeah, we must be computing several times the same state. So using this memoization object and memoization technique, we avoid to compute several times the same states. So thank you very much for today. It was a bit more complex than the previous days, so hopefully you're still holding on the challenge. Please drop a like and see you in the next one. Bye.